Uh, my name is Hudson Chakachi. I'm the group leader for Group 7 on the project for the installation of power, renewable energy at a remote village in Reproa in New Zealand. Our project is renewable of electricity supply for remote village. Our project is renewable electricity supply for remote village. Uh, the context and background of the project. ABC is our company that has been contracted by the Minister of Environment and Energy to design a sustainable electricity supply system for a geographically isolated village located in Raparoa, North Island, New Zealand. The village consists of 10 homes with no current grid access. This project will prioritize the use of renewable energy source, solar. Diesel shall be used only for backup supply to ensure supply consistency. Currently, the villagers rely on gas for cooking and water heating, and this will reduce our load demand on the electricity supply. Electricity shall be dedicated to lighting, refrigeration, small appliances, and electronics. The client requires a cost-effective, low-maintenance, and environmentally friendly energy solution to improve the quality of life while supporting the country's carbon emission control targets. Number two, our project scope and boundaries. Uh, the items within our scope are design a hybrid renewable energy system, solar with a diesel generator backup supply, load analysis for 10 residential homes, sizing and selection of key components, i.e. solar panels, batteries, cables, breakers, generator, inverter, energy management and distribution system design, maintenance and system performance recommendations, cost estimation and system layout schematic, risk assessment and mitigation plan. And the items that are out of our scope will be civil works, roads, site leveling, building retrofits or internal household wiring, ongoing operation and maintenance after commissioning. And then our main deliveries are load assessment report per home and total village demand, system design report with component sizing, capital and operating costs estimates, environment impacts and consideration, schematic electrical drawings and system layout, renewable generation costs, focus and performance modeling. Our acceptance criteria is as follows. The system must supply at least 95% of annual electricity demand from solar. The backup supply must cover not more than 5% of annual energy demand. Each household to be supplied with a single phase 230-volt protected by a 25 amp to 35 amp MCB. The system must provide a 24/7 availability and self-sufficient for at least 2 days without sun. It must be compliant with the New Zealand electrical codes and safety standards. And then the major constraints. of the project of the project the system must be low maintenance. The system must be easy to operate by local villagers. Seasonal variability in solar resource availability. Remote location may cause problems to transport and logistics. Design must be completed 4 weeks of project initiation. Yeah, I'm done on my part. And let me hand it over to the next one.
Okay, thank you very much. Yeah, my name is Morasa Chona, and I'll continue with the presentation. Yeah, so in my presentation, I'm going to present to you about the requirement analysis of the system. Yeah, so here is a requirement analysis of the functional specification of this off-grid solar system. Yeah, so the solar system is designed for a remote village with 10 dwellings, and this functional analysis it outlines the function requirements and not the design or the implementation of the system. So in the analysis, we are going to look at the inputs to the system. So number one, we have solar energy input. We have the battery bank storage system. We also have the inverter with the inbuilt charger controller. So this inverter is going to have a communication interface, which is RS485 communication interface for data logging and monitoring. Then it also has some protection features, which is over voltage, under voltage, over current, short circuit, and overheating protection. So the ingress protection of this our inverter that we are going to use will be IP65. Then the other input to the system is the diesel fuel input. So we are going to use a diesel generator, and we are going to use fuel for that diesel generator to act as a backup system. Then our system is going to have a user interface. That user interface will have a touch screen or switches that will be used to control and manage the system. Yeah. We also have the outputs in our functional analysis. So the outputs for the system is electrical output with a voltage of 230 AC plus or minus 10%. And as said earlier on, we are going to have a common distribution junction box, which is going to be which is going to house 25 to 30 amps in Kama circuit breakers for each dwelling or each house. The functions analysis for the system or the what the system is going to perform. One, it will be the primary power supply uh, for the 10 dwellings. So the primary power supply will be the solar panels, and then I will have a backup power management system. We are also going to have a battery bank storage management system and a monitoring and control system. Then the environment that our system is going to work on, uh, it will have an operating temperature of minus 10 degrees to 50 degrees Celsius. The humidity range will be up to 95% and non-condensing. The packaging, housing of the components that will be selected for our project, uh, all outdoor components or system, they are going to have outdoor rated enclosures and mounting structures. We are also going to have weatherproof enclosures for electronic equipment. The structural requirements for our system, we are going to have a PV array placement. The array will have a fixed tilt angle as per site condition for maximum solar absorption. The cable routing, we are going to have an underground cable trench or conduit mounted for durability and safety. Other interconnections will have a central control cabinet with some protection devices, just as earlier alluded. For distribution, individual connections to each household with metering and breakers. Now, the safety requirements for the system: electrical safety or earthing and lightning protection, or AC and DC circuit protected with circuit breakers and fuses. There will be a dedicated grounding and earthing system as per the standards. We are also going. The system will also be provided with a lightning, and an over voltage protection system. For shock hazard prevention, grounding will be done for all metallic structures and equipment. We are also going to have some warning signs and danger labels on all enclosures. For fire safety, we are going to have fire extinguishers near the battery banks, and also the diesel generator. For diesel safety, our diesel will be secured in a vented area. So maintenance requirements. So for our system to be maintained properly, we would need a skilled technician. So the requirement for that skilled technician who will be maintaining the system, he should have basic electronic knowledge for daily operation. He should be certified. He should be a certified technician for annual maintenance, and the spare parts that will be included here, that will be stored on site for eventual maintenance. We'll have some spare fuses, some spare breakers, some inverter fans, and diesel filters will be available on site. The maintenance schedule of our system will be a monthly inspection of PV modules and their wiring. So we'll have a quarterly batteries inspection and a biannual generator servicing. Standards, applicable standards. So applicable standards, when it comes to wiring, our system is going to conform with the IEC 60364 ASNZS 3000 wiring rules, and also IEC 62548 installation of solar panel systems. For the battery systems, our system is going to conform with the IEC 61427-1, the performance of batteries used in the renewable system. For generator installation, that is the genset installation and its safety is going to conform to the ISO standards 8528 series. Then for safety and EMC standards, our system will conform to IEC 6109, safety of power converters for solar panels, and also IEC 61000 EMC standards. Testing and quality assurance of our equipment. Before delivery, our system is going to undergo factory acceptance test for all major components. Then test certificates for inverters, batteries, and generators will be provided. Then our on-site testing of this equipment, we have AC voltage frequency compliance test, our PV module string performance test will be done, the battery charging and discharging functionality test will also be done. Our generator automatic start-stop logic will be checked and tested. Then load simulation for peak operation will also be done. Documentation requirements. Our system, after installation, is going to provide the maintenance personnel with user manual, which is going to show the system overview, operation, and troubleshooting. So the other manuals, we have the installation manual, which will show diagrams for wiring, components layout, and the system interconnections. We also provide a maintenance logbook, for which the maintenance personnel will do his inspection records, servicing, and performance checks logging. There will also be some compliance certificates that will be given uh, to show that our system conforms to standards. And yeah, so for training, training material will also be given for basic training for the operators and the users of the system. Okay, thank you very much. That was the end of the functional analysis of the system.
Okay, my name is Shailene, and I was taking care of the analysis of alternative solutions. So I chose to choose between, like, which is the best battery bank that we can use. So to identify the most suitable energy storage option for the proposed system, 3 alternatives were evaluated, which are lithium battery, gel battery, and wet lead acid battery. The evaluation considered 5 factors, which are initial cost, efficiency, maintenance, safety, and lifespan. So a weighted grid analysis was applied to compare performance across these criteria. So this is the first analysis where I listed all the batteries and weighted them according to how I thought it was the best. So the lithium battery, the gel battery, and the lead acid battery. And my factors were the initial cost, efficiency, maintenance, safety, and lifespan. And according to the weights, safety, I gave the highest, followed by the lifespan and the efficiency, then maintenance and initial cost. So with this grid analysis, based on the grid analysis, lithium battery scores the highest due to excellent safety, longer lifespan, high efficiency, and minimal maintenance needs, despite higher initial cost. Gel battery comes second with good safety and medium lifespan, and then wet lead acid comes lowest due to higher maintenance needs and safety concerns. I think that's all I had on my task. So I'll leave to the next.
The presenter for task number 4 is not available. Maybe let me just go through it. I'm Hudson Chagachi representing Kelvin. Doing task number 4, solar installation project. That's qualitative risk assessment, carrying out a qualitative risk assessment. And then the context, the project is solar installation project. Our objective is to identify 10 to 12 project-related risks and rate them in terms of likelihood, probability, that's between 1 and 5, and consequences between 1 and 5. That's then the method AS ISO 331 to 1000 2018 qualitative risk assessment using a 5x5 matrix. Right, our right? The risk, we've got risk number 1, written number 1, weighted all the way to number 10. And then our risk description, you write your risk description, and then your its likelihood to happen. If that risk is rated, maybe rated at 3, and then the consequences if that risk has to happen. What are the consequences caused by that risk? And then you've got a risk. What? A risk scale. I'm not mistaken. Yeah. And then you've got a risk level. The level of the risk is rated between low, medium, and high. And then you've got the risk control measure. It's what control can you put that to try and prevent the risk? So you've got different types of controls that you can use, i.e. use reliable suppliers, maintain buffer stock, and monitor supply risk. Or another one, design review, change your design, come up with a new design completely, abandon the one that you've actually do. So it's trying to avoid the risk. And another one, you can have a detailed project scheduling, visible felt leadership, contingency planning, right? These are all. This is all related to projects. All these risks, they are related to projects. Right. And then you've got you've got our risk number 9, change in government incentives and feed-in tariffs post-contract. Okay, then you need to follow that the scale that is written on top there on the risk, the level, and the size, and where do you rate the risk, and then those are the mitigations towards that risk. Right. Next. Right. It goes on and on. We had right. Then we've got our risk matrix there. It's at the 5x5. It shows you the likelihood against the consequences. That's the likelihood is the chance of the risk occurring. Yes, if there is a certain risk that you think of, what are the chances of it happening? And if ever it happens, how severe could the outcomes be if the risk event occurred, right? So that's how you'll be trying to use the risk matrix. So, like, for example, here you've got the likelihood of it, it's almost certain. And then how severe could the outcomes be? The risk event occurred. You find it's insignificant. So which means it's the risk is at medium. It's in our grim. It's not that much. Then you have extreme risk like where you've got the event, the outcome of this event happening being usually when it's red, it's a fatal thing. When it turns red, usually that will be a fatality. So we don't usually want to play in the red. That's why you would rather go back to our things that way you have to change. Go back to the drawing board and change your plans or your strategies. Go back to the drawing board there. Right. Next. Right. The guidance on ratings, likelihood ratings, the rare may occur only in exceptional circumstances. That's less than 5% chance. Unlikely could occur at some time, but not expected, 5 to 20%. Possible might occur at some time, 21 to 50%. Likely will probably occur in most circumstances, 51 to 80%. Almost certain, expected to occur in most circumstances, greater than 80%. Consequence ratings, insignificant, no injuries, low financial loss, negligible impact on objectives, minor first aid treatment, minor financial loss, minimum disruption, moderate, medium medical treatment, moderate financial loss, some disruption to objectives, then major extensive injuries, significant financial loss, major disruption, severe death, that's a huge financial loss, critical impact on objectives. And then monitoring and review, frequency of review, bi-weekly after major incidents, reporting lines, project manager to all project stakeholders, including employees involved, control effectiveness indicators, incident reports, audits, results, compliance rates. This now I hand it over to the guy who's doing the task number 5. May you please take over.
So this document outlines the detailed specifications for an off-grid solar plant in support of a standby diesel generator to supply electricity to Raparoa village in New Zealand. It outlines the system's inputs, outputs, functions, and other essential performance. So on inputs to the system, we've got solar energy, which is the primary source of energy captured by solar panels. And we've got diesel fuel power. We've got diesel fuel. This is the fuel used by the system to power the diesel generator for standby power supply. And we've got user input, which is the user who has got a switching control between solar generator and system monitoring. So we move outputs from the system. From the system, we get electrical energy, which is AC voltage, 3-phase, 380 to 415 volts at 50 hertz frequency. And total power should be 15 kilowatt and maximum current of 60 amps. And the tolerance will be plus or minus 10%. So we move on to system architecture. On system architecture, we've got solar panels, and the chosen panel type, it will be a monocrystalline panel with a pipe number of JM72S30 stroke 550 MR with a maximum power of 550 watt, operating at a voltage of 49.9 volts and operating current 13.11 amps, short circuit current 14 amps, and the dimensions 2279 by 1134 by 35 millimeters, and to be ground mounted with concrete foundation. Then our inverter type, it will be Fox ESS H3 Pro hybrid inverter with a maximum charging or discharging current of 220 amps, And the battery type, supported battery type for this inverter is lithium ion. And the battery voltage range should be 40 to 60 volts. And maximum input power to the inverter, it's 7,500 watts. And maximum PV input voltage, 1000 volts, and MPPT range 150 to 850 volts, and maximum AAC output power 15 kilowatt, maximum rated current 53 amps, and the maximum continuous current for this inverter is 60 amp. Then the output frequency of voltage, it's 50 or 60 hertz, 230 or 400 volts AC 3-phase, at an efficiency of 97.6%, and the communication port RS-45 or CAN, and certification in standards should be it should comply with IEC 21091 and IEC 62109, and the protection degree is going to be IP65. Then our chosen battery bank, the battery type, it will be lithium iron phosphate, SANZIC, and the part number is SSB8015K 15.97 with a nominal voltage of 51.2 volts and 312 AH, and the charge voltage it's 55.68 to 56.16 volts, and the maximum charging or discharging current is 300 amps. Communication port RS32 or RS45 or CAN, and the number of and single string quantity, it's 8 batteries per each string, and certification to be certified under IE62 or IC62619 or IEC 61000. Then on the cables and wiring on the batteries, the cable size would be 70 square millimeter copper with PVC insulation, and the current rating it will be 485 amps voltage rating, 60 volts DC, and PV panel cable size should be 16 square millimeter tint copper or XLPO with XLPO insulation. And the cable that's going to be used from the inverter to main DB, it should be 16 square millimeter copper PVC steel wire armored cable. And from the generator to main DB, it will be 16 square millimeter copper PVC steel wire armored cable. And from DB to overhead lines, we've got we use a 50 square millimeter AC SR conductors, and the service cable should be 16 square millimeter copper cable, and the support structure for overhead lines to be treated wooden poles. And then from AC DB, the DB type to be a 3-phase automatic control panel board. Operating voltage for this DB to be 220 or 415 volts, 50 hertz, with a maximum power of 15 kilowatts, and MCB rating per dwelling should be 25 to 30 amp per dwelling. And on mounting structures, the material types that are going to be used are wood, aluminum, steel, and concrete. And these mounting structures must be corrosion resistant. Then we move on to the functions, detailed functions of the specified components. We've got solar panels. They convert solar to electrical energy, which is DC power sufficient to power the load and charge the batteries to full capacity. So the battery bank will be storing excess energy generated from solar panels for later use, and they must supply power for up to 3 days of autonomy. Then the inverter converts DC input voltage to AC 3-phase 400 volts 50 hertz to power the 10 dwellings. And the AC DB distributes AC power from the inverter and from the generator to various loads. Then the DC generator, it generates 3-phase 450 hertz AC power to supply 10 dwellings in the event of solar system failure. Then the cables and wiring, they transmit electrical energy between components, ensuring safe and efficient power distribution. Then the support structures will be providing mechanical support and protection for cables, and mounting structure will support and secure solar panels, distribution boards, and other components in the system. Then we've got a storage container for all those components. It protects and houses batteries, inverter, and other components, providing a safe environment and improved component lifespan. So we'll also have a generator shade, which protects the generator from harsh environmental conditions and enhance security for the generator. Then we have a control room, which serves as a central hub for monitoring, controlling, and managing systems performance, allowing operators to oversee and optimize energy production.
Johannes, I think we must just read headings because we're way over time here, so we need to rush a bit. So just go through the headings.
Sorry. Okay, I can continue on the system environment. On those components, the operating temperature be minus 10 to 50 degrees with humidity up to 95% relative humidity, non-condensing, protection degree 65, and the fire protection system. We use a passive and active fire protection system. So let's move on to the next stage, which is system packaging. The material should be stainless steel SS304 and IP rating of greater than or equal to 65. And the ventilation, we've got breathing fans with insect-proof screens and temper lock resistance locking system. And on cable management, we've got PVC conduit trunkings, cable ties, and glands to secure wiring. And there must be clear labeling of wiring components and safety information. Then on the system structure, it was shown as a block diagram. We've got solar panels which supply power, DC power to the inverter, and the inverter converts the DC to AC, and it goes through the changeover switch and then go to distribution board. Then from distribution board, we supply our 10 dwellings. Then the inverter also charges the batteries, and it will be communicating with the control room. Then we've got the DC generator. It will be there will be communication between the generator and the control room. And the generator, it supplies power straight to the changeover switch and to the main DB. And we also have provision for metering going back to the control room. That's the basic system structure. Then let's move on to system behavior. System behavior is the interaction and linkage of components and how they behave under different operating conditions. So the diagram below illustrates various operating states, transition, and the logic that govern the system's operation, highlighting the relationships between components and their responses to changes in the system. So it was shown in form of a state diagram. So we start on the idle state. Then after that, when the sun rises, the solar power becomes active. And when the solar power becomes active, it supplies the load, and excess power will charge the batteries. And when we've got low solar, batteries will start discharging because they're supplying the load. And when the batteries become low, the generator comes in. And in the event of solar system fault, that fault is detected and it triggers the generator active state. And when the fault is clear, it will go back to the idle state when we can decide which source to use. And it will be decided by the operators. Thank you all. That's the end of task number 5.
That's for you, Sender.
Oh, sorry, I didn't unmute. Oh, sorry. Okay, thanks for letting me speak. Yeah, basically, I'm a bit rushed for time now. Our work breakdown structure is as follows: 5 main headings, as you can see. Basically, feasibility study, procurement, construction, commissioning, and client acceptance. And then under those various headings, you can see there we have all those various functions that we have to comply with before we can move on to the next. So basically 1.2 follows 1.1, 1.3 follows 1.2, and so on. So it's just each task or major task follows on from each other. And then due to some, yeah, so you can see the detail there. We've added start and finish dates and basically the duration of the project to see how long it's going to take. And if all tasks are finished on time, we should all make it on time. And then, sorry, due to some unforeseen technical issues, the PERT and Gantt charts have not been uploaded. So we will not be able to show those. But basically, if you just follow these dates, you can see how the project flows. And thank you very much. I hope you enjoyed that. Over to you, Hudson.
Yeah, that brings us back. That brings us to the end of our presentation. I will stop